Hello everyone, welcome to the new episode of Generative Geek. Today's topic is vector databases. Vector databases are very important if you are thinking about building LLM applications. All of the embeddings that you do, every text that you want to ingest has to be stored somewhere. And when you're working with machine learning, NLP, LLMs, the way it has to be stored is such that the machine and the model are able to get insights from the text that you have ingested. What I mean by insight here is that they should be able to get context and intent from the text. One way we have been, I've been doing several videos on embedding. One way models achieve that is by calling the embedding model, and that embedding model basically takes the text and puts it into a vector space, right? So today's lecture is about vector databases. My goal here is to see how we can, how I can help you today understand what vector databases are. Today's session is going to be all about theory, but we'll do it in a very visual way so that you are able to understand most of it. So I'll cover what are vector databases, how do they differ from traditional databases, how do you store data using vector DBs, then once you have stored data, how do you actually get your data back, what is the query and retrieving mechanism. And one logical thing is, if you are storing embeddings for every vector and you're doing queries on every vector, as the database grows big, there are going to be issues around latency. So how do you solve for that, right? How do you ensure that you are actually not getting stuck in the latency? So role of indexes becomes important. And then lastly, I'll cover some popular vector DBs. We have a full session coming up on Chroma DB later. But I'll just walk you through what are the popular vector DBs available today. So without further ado, let's get started. So what are vector databases? Well, vector databases store information as vector embeddings, right? So like I said, what happens is when you have a lot of unstructured data, that data has some sort of meaning, right? Because it's not like you are just randomly inserting something. You have some text. Maybe you have a lot of books you want to ingest. Maybe you have a lot of medical records that you want to ingest. Maybe there are a lot of images that you have gathered, right? There are videos, there are audios. Now, for the machine, it's just a plain file. But the moment you do embeddings on it, the model can do some inferences, figure out what you are trying to do, and create vectors out of that text, right? Out of that text, in the sense, even if it's an audio, you will take the audio, you will convert it into some sort of a raw file, and then pass that raw file of, let's just say, an array, a NumPy array or something like that. You will pass that to the embedding model to actually get embeddings from the model, right? And what the model will do is it will convert that. It will find the vectors that that particular text or particular array or particular list that you have sent. What are the various vectors that correspond to that text, and it will pass you back that text, right? Pass you back that embedding. Now that embedding is actually a dense vector space where model, it's up to the model, right? The model understands that it has given you a certain vector back. What was the logic behind it? That's embedding models, internal logic, right? But the way the models work is that, if I send two very similar data points, right? Two very similar sentences, two very similar audio files, and I don't mean similar in the sense, hey, if I say cat and the other guy also says cat, that those are similar in the sense of context and intent, right? So if we are both saying the same thing but in very different words, the model can still figure out what is the context and intent, and those two vectors are going to get placed very close to each other. So that's how it helps you find similar data quickly and easily. So coming back to what are vector databases, they will store your information as vector embeddings, and the way they store it is that the storage is basically a mathematical construct. It figures out where should this vector go, and it'll put that vector somewhere, right, in that space. Next, when a new vector is coming in, it will say, hey, you know what, okay, based on what the vector is, I'm going to place it at that location Y, right? So that's how it is going to keep placing the vectors. Now, embeddings of text help the large language models understand context and intent of the text, right? So vector database is basically, in short, if you have to quickly understand, they will store your embeddings and they will help you do a lot of similarity searches. They will help you give it a query, it will figure out if you have relevant text ingested already, it will give you that text back, it will give you the embedding, and then using the embedding you can get the text back. So this is what the vector database is, at a very broad level do. Now, the next topic is that, how does vector database actually differ from a traditional database? Now, if you look at a traditional database, they work in a way that, you give them some information and they will store that information in the database, right? So generally it's structured data. Even if it's a PDF or an image or a document or an audio file, the database is not trying to figure out what is the content or what is the intent. Even if it is looking at the content, it is looking at the content in a very structured way. Hey, how many times was cat uttered in this sentence, right? So things like that. Now, you pass those documents to the database. Generally, what you do when you are building applications, you don't pass the PDF itself. You will store the PDF or the image or the document or the audio file somewhere in some storage location, and that storage location's reference is what you will put into the database, right? And this is the way that traditional databases, they store references of files, but they treat all of the data that is coming into them as structured data, right? So structured here refers to information that follows a predefined schema, right? So if your schema is predefined, if it's mostly like a form fill, like, applications were built, have been built till now, where they ask you to submit certain information in a very certain way. Please write your first name here. Please write your last name here. Please write your email address here. Your password has to be in a certain way. This is the place where you're going to upload that document, right? So, and what is happening behind the scene is, as you're aware, it takes all that data and then stores it in the database, right? So if it's structured data, you generally went with traditional databases. So there was, there are traditional databases, they store data as structured tables, while vector databases, they represent data as a high dimensional vector. The querying mechanism is also very different, where, in case of a traditional database, you generally use SQLs for querying structured data, whereas vector databases, they employ some sort of similarity search based on vector proximity. Again, scalability, vector databases are designed to handle large scale unstructured data, whereas traditional databases generally, even if it's a NoSQL database, NoSQL is where you don't have a structure, but you still have a structure. Structure in the sense, the structure is controlled by the application there. The database is capable of ingesting whatever you give it, right? So it's like a JSON. You just give whatever keys you want. Some keys are probably mandatory, but you give as many keys as you want. You can create new keys and it'll be okay, right? Vector database, on the other hand, is more about taking unstructured data, doing some sort of an embedding on it. And what I mean by embedding here is, like, I've been talking about it. You use an embedding function and you create vector representation of it. So it's no more a PDF that is getting ingested. It's some sort of a long string of numbers, long list of numbers, which is basically how the model thinks that, this certain sentence in the PDF or maybe a large paragraph in the PDF should be represented. And then it goes out and it gets saved into a multi-dimensional vector space, right? So the model will decide that, hey, this is what the vector representation looks like. It'll hand it off to the vector database. The database then sees it and says, hey, you know what? Based on what I'm seeing right now, I would like to put it in that shelf, right? And that shelf is not like a 2D shelf. It's a multi-dimensional shelf. So it can have, like, several dimensions, like thousands, right? So it'll decide what those various values will be basis what it sees, and it'll store it there, right? And when it is storing, its objective is very clear. Its objective is that, hey, I want to store it in a way that I'll cluster similar values closer to each other, right? So that's the way. If I can store it in a way where I'm applying some mind, I'm not just randomly putting it wherever I want. When it comes to retrievals, it will be easier for me, right? So that's generally the logic that the database designers design, right? They basically put that they're like, hey, you know what, we have a multi-dimensional space, but this is how we are going to assign this space. It's like a locker, right? Hey, so it says, hey, you know what, basis what envelope you are sending towards me, I'll read that envelope and then say, hey, you know what, okay, you go there. That is the drawer that I'm allocating you. And that drawer is not like a linear or horizontal row of drawers. It's like a multi-dimensional row, right? Multi-dimensional space. So this is how it works. Now, once you have stored, you want to now get back the data, right? So how does it work? So let's just assume a user types in a text query. User says, hey, you know what? I want to figure out how many red color shoes, what is the price of red color shoes for kids, right? Let's just say if we had ingested a product catalog and this is the query that is coming in natural language. One thing that I kind of missed is that, you know, there are several embedding functions. So when you are storing something into the vector space, into the vector database, you need to kind of know what was the embedding function that you used, right? So, and that you need to know, because you obviously know, but you need to record it somewhere that, hey, we are using this specific embedding function when we are storing data into this collection in a vector database, right? So, and why it's important is because, you know, when you want to now query something, the query is coming in, let's just say in some language, maybe in English or Hindi or Spanish or Persian or whatever, right? But that text query has to be converted into those vector representations. And if you want to convert it back into a vector representation, you need to know what was the original embedding function, right? Because let's just say for storing you used OpenAI's embedding function, but when you want to query, you are using Google Gemini's embedding function, or you may be using Word2Vec or something like that, some other model. What will happen is your embeddings are going to look very different, right? So when you send that vector, so once the embedding function creates those vectors, the next step is that, you know, that vector is taken by the database and compared in various drawers, the multi-dimensional space it has. It compares that, hey, what are the most similar or the nearest neighbors of this vector, right? You know, I might not have this specific vector, but who are my nearest neighbors, right? So it's like you make a call to the main desk of an apartment which has like 1,000 families living, and you ask them that, hey, you know what, do you have anyone by the name of Pandey, right? And they might say, hey, you know what, I don't know, but if you tell me, if you give me a minute, I'll just find out. So they will just say, hey, you know what, how many people who have last surname as Pandey? That's like a very traditional database query where I'm doing an exact match. But let's just say if they had said, hey, do you have any Asian man who's in his 30s or 40s and who's around 5 feet 10 inches? Then the model is going to go out, look inside, like, you know, this query is going to get converted into an embedding, and that vector representation is then going to get searched inside and say, hey, you know what, I found 3 people who look similar to what you are asking, right? And then it is going to return profiles of those 3 people. Now, it was not a very exact match. It was converted into something that the model understood, and that's how it works, right? So that's what we are doing here. So once you convert the embedding, once it's in a vector representation, you're trying to find the nearest neighbors from the multi-dimensional space. Once you have those neighbors, and, you know, the way to compute these neighbors is there are 2 popular algorithms. One is the cosine distance, where you basically look at the vector and all other vectors inside and say, hey, you know, what is the angle between these 2 vectors? Cos of 0 is 1, so cosine of 0 is 1, cosine of 90 is 0. So more the angle, farther away they are. but smaller the angle, more similar they are, right? So, and Euclidean distance is where you just look at a straight line distance between two vectors and say, hey, so smaller angles means lower cosine distance. Lower Euclidean distance means more similar, more nearer, right? So once you have those embeddings, what happens is you generally get back the text from most of the databases. But let's just say if you were storing it in a database and you were getting only the embeddings back, the internal working is that there is some sort of a post-processing now happening where from the vectors, because you know the embedding function, you are getting the text back, right? So instead of just returning the vectors, you are now converting back into text, and that result is then sent back to the user. That is how basically this whole thing works, right? I hope you understood. If you did not, if there are any questions, feel free to write in comments. I'll be very happy to answer. Now, think of this case that, where you have this multi-dimensional space and you are just filling in all the drawers, right? You're continuously filling them with all the new embedding vectors that you're creating. You are ingesting tons of data. If this was like an exhaustive search where an incoming vector, let's just say an incoming vector, it is getting compared with all the vectors in this space let's just say I get an envelope and I'm trying to compare it against all the envelopes that are stored in my drawers. It's going to be an exhaustive search, right? And this doesn't augur well as the database, as you keep filling in the drawers. If there are infinite drawers and keep filling all the drawers, this doesn't seem to augur well, right? With latency. So the way to work out is that, how do you actually store data such that when the database size grows, comparing incoming vector with each stored vector does not lead to latency. And the question to ask is, do you even need to compare each vector with every other vector, right? So indexing generally addresses this problem by creating a special data structure that organizes the vectors in a way that allows for faster retrieval of similar vectors. So think of it this way, that if you have a very large problem space, indexing basically narrows your problem space down. Instead of searching the massive Pacific Ocean, you are only searching a specific area, maybe a few kilometers of area within that ocean, right? So that search is going to be obviously much narrower and will not lead to the kind of latencies that you will get if you are comparing against everything, right? So indexing techniques that are very popular are approximate nearest neighbor, product quantization, inverted file indexes, tree-based indexes. These are these are some specifically designed algorithms which optimize similarity searches. Again, the core here is that you want to find nearest similar neighbors, right? So you want to optimize that, and there are a few ways. These are basically those algorithms. I'm not getting into some of these algorithms right now, but as part of the description of this this video, you will find a link to the blog, and that blog I have tried to explain how product quantization works, how approximate nearest neighbor algorithms work. The more important thing here is that when you are trying to narrow the problem space, there is a trade-off, right? So there is some accuracy getting traded off, right? There is always a chance that maybe the most similar guy was not even covered because you narrowed the problem space. Now that happens, but the goal here is that, hey, can I be still very accurate, if not most accurate? Can I still be highly accurate and return the result in a very with speed improvements, such that when it comes to large vector databases, working in production environments or working on very large data sets, they are still useful, right? If it takes forever for one query to return results, and even if that result is great, it won't make a production use case, right? So this is where what this does. And now some popular vector databases are Pinecone, Chroma, Faiss. We'll be covering a lot of these databases in our future lectures. We're going to go hands-on in Python creating these databases. I've already written a blog on ChromaDB on my blog mindfulcto.com. A link is there in this blog, in this, as part of the description on this YouTube channel. Have a look at that. And in future videos we are going to create LLM apps which will store embedding data into Chroma, embedding data into Faiss, Pinecone, and all that, right? So we'll do that. Thank you. I hope you learned something new. It's my humble attempt that I bring new content to you, and if you liked it, please do share, like, subscribe. That will be very, very helpful, and very appreciative. I'll sincerely appreciate your effort there. Thank you so much. Thank you.